So in today's session we'll be discussing about chemical kinetics. In previous class you are already familiar about the rate of the reaction, units of rate of the reaction, order, molecularity, and you also discussed various factors which affect the rate of the reaction. Okay, there you might have observed that concentration dependence of rate is a differential equation. So when you get a differential equation, what happens is it becomes difficult to determine the rate law as well as the order. Okay, so what we will do is, in order to simplify that, we will integrate the differential equation. We will integrate the differential equation so that it is experimental with the, so that it is compatible with the experimental data. Okay, so now what we will be doing is, we will be first deriving the integrated rate equation for the zero order reaction, then we will go for the first order reaction. So as you know, the integrated rate equations will be different for the reaction of different orders. Okay, so first let me tell you what is a zero order reaction. So if you consider a simple reaction like this, are giving products. Okay, now if you are asked to write the rate of this reaction, okay, so rate is equal to K into concentration of R to the power 0. So that means for a zero order reaction, what happens is rate of the reaction is directly proportional to the zeroth power of the concentration of the reactant. Okay, so with this in mind, what we will be doing is we will be deriving the integrated rate equation for the zero order reaction. Okay, so consider a zero order reaction like this. Okay, so now I will write it. Integrated rate equation for zero order reaction. Okay, as I told you, we will now consider a zero order reaction. Okay, like this. See, are giving products. Okay, so now we can write rate in two ways. Okay, one is by making use of the rate law. Okay, so how will you write that? Rate is equal to K into R raised to the power 0. Okay, you can also write it in the differential form. So how will you write that? Rate is equal to, see, while writing this you have to be very careful. Okay, you can write either in terms of the reactants or in terms of the products. Okay, so when you write it in terms of reactants, make sure to put a negative sign, because what we know is as time proceeds, concentration of the reactant goes on decreasing. Okay, so rate is equal to minus dr divided by dt. So I am using here, I am writing the differential equation in terms of the reactants. So I am using a negative sign here. Now as you can see here, this is also equal to rate and this is also equal to rate. So what I will be doing is I will be equating both. See here, rate is equal to minus dr by dt, that is also equal to K into R raised to the power 0. Okay, so you know that anything raised to the power 0 is 1. So K into 1. So now I will write this as such, dr by dt. So now what I will be doing is, I will be multiplying throughout by minus 1. So what happens now? dr by dt is equal to minus k. Hope you understood this. So now I'll do a bit of rearrangement, that is dr is equal to minus k dt. Okay, so dt I took it to the other side. Okay, now we know that differentiation is always complete by integration. So what I'll be doing is integrating this equation, integrate both sides. So this is a sign of integration, integration of dr is equal to, so k is a constant, so I'll be taking it outside, I'll not be integrating that into integral of dt. Okay, now you know that what is integration of dr. Okay, it's very simple. Let us r is equal to minus k integration of dt is nothing but t plus I. What is I? I is the constant of integration. I is the constant of integration. So now what we have to do is we have to find the value of I. So how to find the value of I? We will just write here to find the value of I. Okay, so what I will be doing is I will be using a simple trick, that is I will put t is equal to 0. Okay, at time t is equal to 0, what is the concentration of R? Concentration of R is, take it as R naught. What is R naught now? R naught is the initial concentration. What is R naught here? R naught is the initial concentration of reactant R. Okay, so this equation I will be taking it as star. I will be substituting for the values of t and r in this particular equation. So what happens now? In the place of r, r becomes r naught, that is equal to minus k into 0 plus I. What is I equal to now? I is equal to R naught. Okay, so hope you understood till here. Now what I will be doing is I will be substituting for I in this equation star. So how do I substitute? Right here. Substitute for I in star. So when you do that, what happens? See, R is equal to minus KT plus R naught. Now what is this? This is the integrated rate equation for the zero order reaction. Okay. So now what I will be doing is I will be finding the value of K from this. Okay. So how to find K? Find K from this. So I will do a bit of rearrangement, that is KT is equal to, bring it to this side, it is R naught minus R. So what is K now? K is equal to R naught minus R divided by T. So here you are getting the expression for the rate constant of first order reaction. So it is very simple. Okay, now what we will be doing is we will be doing some graphical representations. Okay. See here, if you take this equation, so I'll write it again if you want. R is equal to minus Kt plus R naught. Okay, so what does this R tell you? It is concentration of R. This is K, rate constant, T is the time, and what does R naught? It's the initial concentration of R. So you can compare this with the equation of straight line which you might have studied, that is which equation? That is y is equal to mx plus c. You can easily compare it with this. Okay, so as you can see from here, if you compare this and this, you will be able to get x as well as y coordinates. Okay, and so this is the slope and this is the intercept. Okay, so based on this, what I will be doing is, I will be taking y, that means concentration of R on the y axis, and T, that is I will be taking it on the x axis. So I will be plotting graph of concentration of R versus time. So we will do that, see what you get. Here I will take concentration of the reactant, that is nothing but R, and here what I am taking is time. Okay, so when you do this, what happens? See here, slope is negative. Okay, m corresponds to slope. Slope is negative, and you have an intercept also here. This refers to intercept. So what you will be getting is, you will be getting a decreasing line. Okay, like this, getting a negative slope with a negative slope. And what does this intercept give you? This intercept will give you the initial concentration of the reactant. Then from the slope you can easily calculate what is K. Okay, remember always K is the rate constant of the reaction and it is never negative, it is a positive value. Okay, so if you can just write it like this, K is equal to minus slope. Okay, so this is the graphical representation. Okay, now let us discuss few examples for the zero reaction. So the most familiar example for the zero order reaction is nothing but decomposition of ammonia. So decomposition of ammonia occurs on the surface of platinum. It occurs on the surface of platinum. Temperature, high temperature and high pressure. What you get is, when ammonia decomposes, you get N2 and H2. So here it is 2. So equation is balanced, 1130 Kelvin. It's 1130 Kelvin is balanced. Okay, so decomposition of ammonia is a very good example of zero order reaction. Okay, one more example you can consider is decomposition of hydrogen iodide, that is actually thermal decomposition of hydrogen iodide on the surface of gold. Okay, so I will be writing that equation. Hi will give you, decomposes to give you H2 plus I2, so it is 2 here, and then it is a thermal decomposition on the surface of gold. Okay, you followed. Next, so what are other common reactions? See, apart from this, most of the photochemical reactions, for example, it may be the formation of hydrogen chloride, okay, and even several enzyme catalyzed reactions, they all come under zero order reactions. Okay, so with this, hope you understood. We'll move on to the first order. Okay, so similar to zero order reaction. Okay, what we discussed there, rate of the reaction is directly proportional to the zeroth power of the concentration of the reactant. So now here you will be discussing about first order reaction. So the statement is obvious, that is the rate of the reaction is directly proportional to the first power of the concentration of the reactant. Okay, so I will just take a simple example, a unimolecular reaction. So the rate will be like this, K into concentration of the reactant to the power raised to the power 1. So this is a typical first order reaction. Okay, so now what we will be doing is, we will be deriving the integrated rate equation for the first order reaction. Okay, so consider a typical first order reaction like this. Okay, so now rate can be written by considering the rate law. So how will you write that? Rate is equal to K into concentration of the reactant raised to the power 1. So in the zero order case it was concentration raised to the power 0, and now it is concentration raised to the power 1. Okay, so that make a note of this difference. Okay, now so in the differential form, how do you write the rate? Rate can also be written as, so I told you, as in the earlier case you can write it in terms of the reactant as well, but make sure to use a negative sign, that is minus dR by dt. So in the next, what I will be doing is, rate is equal to this, rate is also equal to this. So rate can be written as equal to minus dR by dt is equal to K into concentration of R raised to the power 1. So any number raised to the power 1 is that number itself. So it is nothing but K into R raised to the power 1, it is R itself. Okay. So now as I told you in the earlier case, what we will be doing is, we will be multiplying it by minus 1, the entire thing. So what happens now, dR divided by dt is equal to minus K into R. You understood this? So next what I will be doing is, I will be doing variable matching, because I have to integrate the equation. So how do I do that? See here, dR by R is equal to minus K dt. So hope you understood this. So now what we will be doing is, we will be integrating this. So when you integrate both sides, what happens? Integration of dR by R is equal to minus K. As you know, K is a constant, we are not going to integrate that. So it is, we are going to integrate only this. Okay, as you know here. So what is integration of dx by x? So what is the value of the integral? That is ln x, or you call it as ln x, or you can also call it as natural log of x. So what do you mean by that now? See, whenever we tell log, it means to the base 10. Okay, so whenever you use ln or ln or natural log, it means log to the base e. So we have to be very particular about this, especially while deriving the equation for the first order. Now, so from that, how I will be writing this? I can write this as ln R is equal to minus K. What is the integral of dt? Integral of dt is t plus, I will be writing the integration constant. So what is I here? I is the constant of integration. I is the constant of integration. Okay, now as I told you in the previous case, what you have to do? You have to find the value of I. So we will write here to find the value of I. So how do you find the value of I? So I will take t is equal to, at the time t is equal to 0. What is the concentration of R? At time t is equal to 0, concentration of R is R naught. Okay, that refers to the initial concentration. So again I will write it here just to make it clear again and again, that is R naught refers to the initial concentration of the reactant R. So R refers to the initial concentration of the reactant R. Now what I will be doing is, I will be substituting for T and R in star. So this equation we will take it as star. So in star we will be substituting that. Now look at this, in place of R what I will be doing? I will be writing it as R naught is equal to minus K into. So in place of T what you have to write? 0 and it is I. So what is I equal to now? I is equal to ln R naught, or you can also call it as ln R naught. So in the next step what I will be doing is, I will be substituting for I in star. So how do you substitute? Substitute for I in star. Okay, so when you do that, equation becomes ln R is equal to minus KT plus ln R naught. So in place of I am writing ln R naught. So now this is the integrated rate equation for the first order reaction. So integrated rate equation for the first order reaction. So from this you can find what is K. Okay. So how do you find K now? So we will do a bit of rearrangement. So this minus I will be taking to this side, becomes KT, and this ln R naught, write it as such, minus ln R. Okay. Now what is K? K is equal to 1 by T, and we will do something for this. So what is that thing? So you might have studied the formula of log. See here, if at all it is like log m minus log n. So what it means is log, you can write it as log m by n. So we will be using this one frequently. So make a note of this. Okay. So I will apply this one here. So it does not matter whether it is log or ln. Okay. So you can just apply it here. So what it becomes is ln R naught by R. Okay. So now we have simplified this. Okay. Further, okay, for the calculation of problems and all, if we are not comfortable with the ln, we can convert it to log. So log means it is to the base 10, as I told you in the earlier case. Okay. So how do you do that? So just multiply by 2.303. So when you do that, K becomes 2.303 divided by T log R naught by R. Okay, so this is the expression for the rate constant of first order reaction. Okay, so this is from this we have arrived at this. So from this is the equation. Okay, from that we have derived K. Okay, so now what we will do is we will see in which different forms of writing this equation. Okay, that is the first order integrated rate equation. So I will be making use of this equation, and with a bit of rearrangement I will come to the various other forms, the different ways in which you can write it. Okay. So I will take that particular equation itself, ln R, ln R is equal to minus kT plus ln R naught. So now what I will be doing is I will keep kT there itself, ln R minus ln R naught is equal to, so this I brought this side, so it became minus, is equal to minus kT. Okay, so now here I will be applying this formula of log. So what happens now? It becomes ln R by R naught is equal to minus kT. So now I want to remove this ln or ln. So what I will be doing is I will be taking anti-log on both sides. So how to take the anti-log? You see here, concentration of R. So this will be going to this side. So when you take anti-log, you already know that this is ln means nothing but log to the base e. You have here to the base e. So what becomes as? Becomes e to the power minus kT, concentration of R naught. So just write it finally like this, R is equal to R naught e to the power minus kT. So this is another form of the first order integrated rate equation. Okay, so you can observe that it is exponential. Okay, so what you can infer from this is first order reactions, they are never complete. Okay, they will be occurring and they are never complete. Okay, so next we go to the other form. See, supposing you have different concentrations of R. So that time what will be the rate equation? How to write that? That we will see. Supposing you consider R1 and R2. Okay, these are the concentration this is the R1 and R2. Of the reactant at time T1 and T2. So when you have two different times T1 and T2, let the concentration of the reactant be R1 and R2. Okay, that time what happens to the equation? So again we will be making use of this one. Okay, I will substitute here ln, in place of R I will be writing R1. Okay, then this remains same, K into T1 plus ln R naught. So it's the initial concentration, obviously it is same. Okay, now when the concentration is R2 becomes K. So, time is now T2. Time is T2 now, plus ln R naught. Okay, this I will be taking it as equation 1. This one I take it as equation 2. Okay, now I will subtract 2 from 1. So, ln this one minus ln R2 is equal to, what happens now? Let us minus K T1 minus K T2. You understood this? Okay, now it is minus K T1 minus becomes plus K T2. Okay, so here what I can do is, what is common here? K is common. You can take it outside, write this as T2 minus T1. Okay, simultaneously here I will be applying the formula of log as I told you earlier, that is I will write it as ln concentration of R1 divided by concentration of R2. So, that log m minus log n, that same formula we used it here. So, now what is the expression for K? So, what is K now? K becomes 1 by T2 minus T1, then ln R1 by R2. So, whenever you have two different concentrations of R, okay, so this is how you will be able to find the rate constant. Okay, so with this we will move on to the graphical representations of how you can represent the first order reaction. So, here again I will be coming back to this equation. Okay. So, it is comparable with the equation of the straight line, that is y is equal to mx plus c. So, if you compare the coordinates x and y coordinates, you can easily get, and also you can find the slope as well as the intercept. So, with this in mind, what I will be doing is I will be plotting graph of ln R versus T. Okay. See how you get. Plot a graph like this. Okay. X axis, what is the x coordinate? It is nothing but time. On the y axis you have ln of R. Okay. So, when you plot a graph like this, again you are getting a negative slope here, that means it is a decreasing line, see here like this. Okay. So, from this intercept you will be able to find what is R naught, that is the initial concentration. Then from slope what you will be getting? Minus k. So, you can just rearrange. Okay. So, this is about one graph which is discussed. Okay. Then we will move on to another graph. See, for that we will need to take this equation, rate constant equation, that is k is equal to 2.303 divided by t log of R naught divided by R. Okay. Now, we will do a bit of rearrangement. So, this I will put it on this side, divided by R that is equal to, see here I will take it to the other side, kT divided by 2.303. Hope you understood this. I just left it on the side, T is taken to the other side, then 2.303. Okay, now even this you can compare it with another equation of straight line, that is y is equal to mx. Okay, make a note here, you do not have any intercept. Okay, so how you will get the line? So here you have a positive slope, you do not have a negative sign. So if you compare the equations, you can easily get x and y coordinates. So what I will be doing now is, I will be plotting graph of this versus t. Okay, so we will go for that. So here in the y axis I have this log r naught divided by r, and here you have t on the x axis. So what kind of line we will be getting here? See, slope is positive. Okay, so you will be getting a straight line passing through origin. So from the slope of this line, slope of this line is nothing but k divided by 2.303. So if at all you want to find the rate constant, you can find 2.303 into slope. So you will get the value of k very easily. So there is no intercept here. Okay, so hope this is clear about the first order reactions. Okay, next what we will do is, we will discuss some examples for the first order reaction. So what are few examples? Okay, so first example is, I will be taking hydrogenation of ethene. Okay, that is C2H4 plus H2. So all are gases. So you will be getting C2H6. Okay, this is also gas. Okay, this is one example which is discussed in our book. And next, you can also have decomposition of nitrogen pentoxide. Okay, that is nitrogen pentoxide will decompose to give nitrogen dioxide and oxygen. Okay, so here it is 2 and here it is 4. 4 to I plus 2 times, so it is balanced. Okay, so apart from this, see, we have seen a lot of radioactive disintegration reactions. Okay, it can be whether it is artificial or it is natural. So most of them belong to the first order reaction. Okay, so this is about the first order reaction. And now let us do another important topic, that is half-life. What is now half-life? So we will be discussing what is see what is half-life. Half-life, okay, so you can get some idea by looking at the name itself. So half-life means it is the time during which the concentration of the reactant reduces to exactly half of its initial value. Concentration of the reactant getting reduced to exactly half of its initial value, and the time required for that process you will be calling it as half-life. Okay, so I will just give you examples. If you have got any 100 gram of any sample, okay, so time required for it to become 50 grams. So that you will call it as T half, and the time required for it to become 25 grams, you call it as T half. Time required for it to become half of this, that is 12.5 gram, you call it as T half. Hope you understood now what is the half-life of reaction. Okay. So now what we will be doing is, we will be finding the relation between half-life, it is represented like this, T half, okay, and the concentration, initial concentration of the reactant and the rate constant, okay, for 0 and first order reactions. Okay, so this is what we will be doing here. So, I will just write it. Relation between half-life and rate constant for 0 order reaction. So, how you will be writing this relation? Okay, again we are going to make use of the 0 order integrated rate equation, that is K is equal to R naught minus R divided by T. Okay. As I told you, what is half-life? Time during which concentration becomes half of its initial value. Okay, so now when time T is equal to T half, what happens to the concentration of R? Concentration of the reactant reduces to half of its initial value. So, it becomes R naught divided by 2. Okay. So, now what we will be doing is we will be substituting these values in this. Very simple. So, K is equal to R naught minus R naught by 2 divided by T. So, what is this? 1 minus half. So, it is nothing but concentration of R naught divided by, so here I have to take it as T half, sorry, divided by 2 T half. So, I can just rearrange that and write T half is equal to concentration of, initial concentration of the reactant divided by 2 K. So, you can infer two important things from this. So, what are those two important things? Half-life of a 0 order reaction is directly proportional to the concentration of the reactant, initial concentration of the reactant, and it is inversely proportional to the rate constant. Okay, so, this is very important. Half-life period of a 0 order reaction is directly proportional to the initial concentration of the reactant, and it is inversely proportional to the rate constant K. Okay. So, with this we have derived the relationship for the 0 order reaction. So, now we will move on to the first order reaction. So, relation between half-life and rate constant for the which reaction? First order reaction. First order reaction. So, again for this I will be taking the expression for K. So, K is equal to 2.303 divided by T log of concentration of R naught divided by R. Okay. So, what happens during half-life? Concentration of the reactant reduces to half of its initial value. So, when T is equal to T half, what happens to R? R becomes R naught by 2. Okay. So, now I will be substituting the values here. See here, so T half I will take it to the other side, it will be very easy then. T half is equal to, K will come here, 2.303 divided by K, 303 divided by K, then log of R naught divided by, So, what is this in place of R? What I will be writing is R naught writing R naught by 2. Okay. So, what happens? Gets cancelled. So, it is 2.303 divided by K log 2. So, log 2 we are all familiar with that. So, it is 2.303 divided by K into 0.3010. So, the value comes out to be 0.693 divided by K. So, T half for the first order reaction is given by this expression. As you can see here, what is happening here if you compare it with the zero order reaction? T half for the first order reaction is independent of the initial concentration of the reactant. So, it is a very important point to be noted, and it is inversely proportional to the rate constant. So, if you know the rate constant for the first order reaction, easily you can find what is T half. Okay, if you know T half, you can find K. Okay. And as you can see here, it is independent of the initial concentration. That means, say I will just give you an example. If you start with some 1 kg of polonium, start with 1 kg of polonium. Okay. So, half life, that means time during which it becomes 500 grams, be something around 138 days or something like that. Okay. This, then suppose you take just 12 grams of polonium, just take 12 grams of polonium, and for it to get reduced to exactly half of it, that is 6 gram, you need T half is the same in both the cases. So, what this tells you is T half is same in both the cases. So, what this tells you? It is independent, T half is independent of the initial concentrations. Okay. And you can also actually draw a graph. Sometimes be given a graph like this, plot of T half versus concentration of initial concentration of the reactant. So, what you will be getting is be getting a straight line parallel to x axis. Okay, sometimes they will give you only this and they will just ask you to write the order. Okay. So, this is straight line which is parallel to x axis. That means T half is independent of the initial concentration of the reactant. So, you will be asked to write the order. So, what is the order? Order is 1. So, be able to answer such questions also. So, these are the two important consequences of this. Okay, T half is equal to 0.693 by K. Okay. Next. Finally, we will be discussing about pseudo first order reactions. So, what is a pseudo first order? Pseudo means false. See, you consider a reaction like this, okay? Take a reaction like this, A plus B giving products. So, if you are asked to write the rate, okay, rate can be written like this, rate is equal to K into concentration of A, concentration of B. Okay. Suppose B is taken in a very large excess. Does it affect the rate of the reaction? No, does not affect the rate of the reaction whenever one of the reactant is present in very large excess. Okay, rate of the reaction will not be altered by the presence of that reactant. Okay, so in that case, see, suppose I will just give you an example. Okay, if it is, say at time t is equal to 0, concentration of A, let it be 0.01 mole, concentration of B, let it be 10 moles, and this one let it be 0. Okay, so when the reaction is just started, product is not there, so it is 0. And after time t, what happens? This will get reduced. What about this? This will become 9.99. Just it is 9.99, and here it is 0.01 mole. So you can just see, even after the reaction is complete, it does not make any considerable difference, okay, with respect to the concentration of B. So what you can do is, you can take any change in the concentration of B to be a constant. Okay, so what I will do is, I just club both and write. So I will just write like this. Take it as a new constant, that is K dash. I can write it as K dash of A. So now, as you can see, the rate of the reaction is dependent only on the concentration of A. So higher order reactions, so if you consider there are many such higher order reactions in which when one of the reactant is present in a large excess, okay, the rate of the reaction is not altered by the change in the concentration of that particular reactant. Okay, in that case, the order becomes, or order reduces to first order. Okay, such reactions you will be calling it as pseudo first order reactions. And you can also note one more thing here. Here the molecularity is 2, so it can also be more than 2, but the order is always 1. Okay, so when one of the reactant is present in a very large excess. So this is about the pseudo first order reaction. So we will discuss a few examples which is given in our book. That is, first example is acid hydrolysis of ethyl acetate. Acid hydrolysis of ethyl acetate. So what happens? We will see to write the equation CH3 COO C2 H5. So I told you hydrolysis. So water, acid hydrolysis in the presence of acid. So what happens? Hydrolysis occurs here. Okay, we get CH3 COOH, that is acetic acid, and then ethyl alcohol C2 H5 OH. So getting this. So if you are asked to write the rate of this reaction, so rate can be written as K into concentration of ethyl acetate and two reactants here, water. So but when in this case what is happening? Water is present in a large excess. So any change in the concentration of water is not altering the rate. Okay. So what you can do? You can take any change in the concentration of water to be a constant. So you can write like this: K concentration of water is equal to new constant, that is K dash. So it is K dash to CH3. Okay, so rate is depending only on the concentration of only one reactant. Okay, so apart from this, we also can take one more example, that is nothing but inversion of cane sugar. Inversion of cane sugar. So inversion of cane sugar is you will be getting glucose and fructose. So this is also another example of pseudo first order reaction. Okay, hope you understood this.